All right. Y'all are all here. Woohoo. Let's cover routing protocols and concepts. We're going to talk a little bit about routing and packet forwarding. Then we're going to get into default and static routes. What is the purpose of a router? Simple. It's just a computer that takes packets from one section and delivers to another network segment. That's what a router does, is it routes that packet using the least costly method or the fastest method. Okay? Routers usually have two different types of connectors. They have their WAN connectors, which would be your backbone connectors, whether it be coming in through a serial connection, fiber optic cable, whatever. And those are connected to your ISP or your internet service provider. Then you have your LAN connections, which is what connects to your switches to feed up your network. Okay. Data is sent in form of packets between two end devices. There's multiple segments that it can go through. All the router does is read the header information to determine where that packet and to which segment it needs to go to. It looks at looks at the packet's destination IP address to determine the best path. Remember, you may have more than one path to that destination. It's going to determine which path is going to be the quickest and best for that to go. A router acts like a computer in the following methods. It has a CPU. In other words, it has a device processing unit that will execute operating system instructions. You have the random access memory, which y'all are all familiar with, right? Y'all have all taken a micro hardware class. Random access memory, if your power goes out, you lose what's in RAM. Okay. ROM is the opposite. When the power goes out, it stays in there. Okay. It's read-only memory. It means it's programmable. You can't write to it like you can with RAM. Then you have non-volatile RAM, which is just holds your startup configuration file, and it can include your host name, your IP address, things of that nature of your router. What does NVRAM do? It is just a little ROM chip, essentially, that helps to boot into this environment on the iOS. Flash memory contains the Cisco iOS, or your router's iOS, and then your interfaces. You can have WANs, serials, Ethernets, console or auxiliary ports, which are what we call management interfaces. Everyone kind of get an idea of that? Right? Here's just an idea of what you might see on the board. You're going to have your slot for your WICs and your HWICs or your VWICs, a couple modules. Then you'll have your fast Ethernet ports. You'll have some RAM in there. Here's your CPU and system controls. You have your user interface, your compact flash memory card if you need extra memory. Here's some more built-in flash, and then you have your boot ROM and your NVRAM. There are three different phases. You have your power off self-test. What does it do? It kicks into bootstrap, right? Once all the hardware is passed, it kicks into bootstrap, similar to how you have power on self-test for Linux or Windows. You have make sure that all the hardware can function correctly with the operating system. Then it kicks in what we call a bootloader. Same thing as or the bootstrap loader. Same thing as a bootloader in Unix or in Windows. Make sense? Have I lost anyone? Matthew? Mitchell? You got it? Okay. Cisco iOS is stored on flash memory, or it can be uploaded from a TFTP server. One of the two. Anyone know what TFTP means? It's what?
Is that FTP?
Well, it's an FTP server, but what does the T stand for? Nope. Trivial. It means it sends it in small packets. It's not meant for big, bulky FTP transfers. Okay? It can send a 64 kilobit operating system over. That's pretty small, isn't it? Then you have a choice of three different ways. You can do NVRAM. You can do it from the console, or you can do it from a TFTP server. The running configuration. Okay? What is automatically put into running configuration when you first turn on a router? Michelle, what do you think? Matthew? What default? No. What do you think, Lance? Don't know. Brandon, what do you think? This configuration file is whatever the start was. Your startup configuration file in NVRAM. Remember, we just talked about that. Your NVRAM holds your startup configuration file. That is what is loaded into your running config when you boot on your router. So if you copy your running config back to start, next time you log on, that NVRAM will use that as the configuration. Does that make sense? You can also pull the configuration from, if there's nothing in the NVRAM, you can pull it from a TFTP server. If it's nothing there, then you can actually create it from the console, which is what y'all are doing with all the command line interfaces. You're setting up your first configuration. All right? How does the router run on this computer? Well, the first thing it does, when you look at the show version, this will give you information on there. It'll give you a platform model number. It's going to give you an iOS version. It'll give you the bootstrap version, the image file name and where it was loaded from, whether it was a TFTP server, compact flash, whatever. The number and types of interfaces, how much NVRAM you have, how much flash you have in the configuration register. Changing the configuration register can change the way you log on. Okay? So your iOS version, when you click on show version or type it out, it'll show you that you're having iOS on a 2600 software. And there's your version 12.2, right? Release 28? Or is it release 5? I can't see from here. And then you have your ROM, your bootstrap, right? That's what loads your boot in. Your model and CPU, this happened to be a 2621 router. Okay? And it's only using 60, it's using quite a bit of memory in it. Out of the 60, 416, it's using 5,120 kilobits. Booting to this 0200. Okay? But anyway, that's where you can get all that information from. Here's what we call management interfaces right here, your console and your auxiliary ports. They're usually side by side. Console will always be blue. Why? Because the console cable or rollover cable is blue. Makes sense, right? Black is your auxiliary. Your Ethernets will always be yellow. Your WAN connections will always be in this bright blue. Okay, these are your mini serials. Not going to really talk about that. We already know WAN interfaces are... you could use it at layer 2 if you needed to, but mainly it's layer 3. And then your Ethernet, the same way, layer 2 and layer 3. Okay? I'm not going to cover... Okay, routers in the network layer. Routers use that destination IP address to get to the destination, right? When you send a packet, it says, I need to go to this IP address. The router reads it, sends it on. So here's a better picture of it. PC1 creates the packet down to the bits. It comes up to the network on this first router, reads it and says, oh, okay, well, I know it's this IP address needs to go out dot 1 to go over to dot 2. So that's where it sends it. That next router reads it, says, oh, okay, I know where it needs to go. So it sends it out, recompiles it, sends it out. The next one gets it, uncompiles it, reads it, sends it out to that final destination. Does that make sense? So it doesn't have to go all the way back up to application to read it. It just comes up to the layer of the OSI model it needs to be able to forward the packet. Does that make sense? Have I lost anybody? Configuring devices with implementing basic address schemes. Okay. We have PC1. This is going to be right here. It's going to be a 192.168.1.10, right? Because that's PC1's IP address. So all you have to do is just figure out what's what and put them in where. I mean, it's pretty simple. Y'all been doing that with subnetting, right? Knowing what networks need to go where. Basic configurations of a router. Now, this is where you really need to start paying attention. Router name. Okay. The command for that is called host name. You want to make sure it's unique so you can identify your router, but you can also say description and give it more of a longer term description if you need to. Banner. That's what the user sees when they first log in. This is an unauthorized system, blah, 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 you know. Passwords. You want to make sure that you enforce strong passwords. And then you also do interface configurations. Those are basic router things that you do with, okay? Once you verify your basic configuration and router, you want to save those changes. How do you save it? You save your run to start. Save your running configuration back to start, so it saves those changes you've just made.
Is it copy run start, or that's different?
Copy run start, exactly what it is. So here's how we do it. To name the router, host underneath the config, you've gone in and you've gone through the enable command to make it a bigger, get into your configuration area or into enable privilege mode. Then you go into configuration mode, you type in host name and then you give it a name. Setting passwords. You enable secret password, okay? Then you can go line console 0, password, whatever you want to call the password, log in, line VTY04. Do the password, log in. Why is it important to say log in? Because you're identifying the password is what you have to do to log in with. Configuring the message of the day banner. The banner. So from configuration mode, you type in banner, hit the hashtag. I'm sorry, banner, message of the day, MOTD. Then hit the hashtag key, the pound symbol. Whatever message you want, then hit the pound symbol again. So what's inside those pound symbols is what's going to be seen. Does that make sense? Save the changes on the router. Start, copy, running config to startup config. Now if you want to see those changes, you can just say show running config. But let me back up a step. Right here, when you're saving these changes, you're back in just enabled mode. You're not in configuration mode. All right? That's where anytime you need to show something so you can see configuration, you need to be back in privileged mode. And we just talked about the show run, show startup config. Show IP route will show you your routing table. Show interfaces will show all the interfaces and their connectivities and what IP addresses and all that stuff are on those. Show IP interface brief just gives you a smaller version of show interfaces. Okay? Routing table structure basically is going to give you different things. It's going to tell you directly connected networks, remotely connected networks, and detailed information. You do that by saying show IP route. So here's an example of an IP route. S means it's a static. Y'all remember the static routes we've done before, right? C's are the directly connected. So it sees .1 and .2 because they're directly connected to here. It can see this router can see this segment and it can see this segment. However, it can't see this segment. So what does it have to do? I'm saying I need to do a static route going out port 1 via port .2. So it'll be a 192.168.30.255.255.255.0 out .1, and that will give me the 192.168.22. That's where it's going to. Does that make sense? Because that's the only thing directly connected out that .1 is that .2. So that's the next hop. Also, when you're on the router interfaces, when you're doing an interface configuration, you want to make sure you always put no shutdown, because by default, everything's administratively shut down unless you say no shutdown. Okay, static routes are denoted by the letter S. S meaning static, right? It'll include the network address and subnet mask via CIDR number and the IP address of the next hop that it's going to, not the hop that it came out of, or not out of the port that it came out of. Does that make sense? Like I said, this 2.2 is going to here. That's that next hop. It's not 2.1. Dynamic routing, basically it adds remote networks to your routing table. Allows you to see those networks and be able to make a better forwarding decisions. Why do you not want to use static all the time? Because the router can't see to the opposite end as well as it can if they're dynamic. Because I can see what's beyond that next network hop on a dynamic routing. So with dynamic routing, we have what we call RIP, IGRP, EIGRP, and OSPF. Okay? And we'll talk a little bit more about those as we finish out this semester in how you program in doing those dynamic routing tables. Okay? There are 3 basic principles that you need to know when you're doing a routing table. Every router makes its own decisions. It's just like a wife. Okay? Makes their own decisions and you have to live with it. A different routing table may have a different information. And it may get somewhere a little quicker. Okay? That's your wife's best friend. A routing table can tell you how to get to a destination, but it cannot tell you how to get back. That's just women in general. Right? No, just kidding. Why can't it tell you how to get back? Because it only knows to the next hop. It doesn't know what's on beyond that. So if you go beyond that next hop, it doesn't know how you got back, right? So that's why the path coming back may be different than the path going. It's like taking I-40 to go to California, but you want to get down to San Diego. Okay? Well, you take I-40, you go all the way out to Las Vegas area and then start going back down south towards I-10, right? You may come back I-10 until you get just east of El Paso and it breaks off, take I-20, come up to Dallas, take I-35 to come back up to Oklahoma City, right? You can do that. So there's a lot of different ways you can go. But it doesn't tell you how to come back the way you went. All right? So here's an example. You have PC1, PC2. We're trying to send message to PC3. Or PC1 is going to send a ping to PC3. It comes out to this first router. Which path is it going to take? It could take this one or this one. Right? Well, let's say it comes to here. Now, is it going to take this one and come down? Is it going to take this one and come down? Is it going to take this one and go over? Is it going to take this one and go back up and down and over? You don't know. Right? Or you can go use all the lines. Discrete math, right?
Is nothing to control that? Where to go? Because if it's something like this, it would not create a problem like a speed and stuff.
More hops. More hops you go through, the less time it has to live. Fields that are important for you to know: your source address, your destination address, your time to live, and your version. So if you pull out that IP packet, you need to know the version, your time to live, your source address, and destination address. You know that, then you can figure out anything you need to know about the route. There's some forensic stuff for you. Hint, hint, hint. Okay, MAC layer frame format. What does MAC layer do? Well, it takes your destination address, your source address, and encapsulates it. It's pretty much the same thing as an IP packet. A metric. That is what we use to define the speed or the hop count to get to the path of least resistance, right? Electricity always wants to run the path of least resistance. Okay? So we have two types of metric. We have bandwidth, which is the speed of our link, T1, 56K dial-up, okay? Then we have another one called the hop count. How many times have you seen a ping? It takes 22 hops. Time to live is 30, and then you see it die off of about 27, right? Y'all seen that before? When you ping something? That's based on a hop count. Okay? An equal cost metric is the condition where the router has multiple paths to the same destination where they have the exact same level. So, what we can do this is called load balancing. All right? You come to router A, you're trying to get to router B. But it can go through C or it can go through D to get to B. All segments have the exact same speed. So router A, you would do equal cost load balancing so that message A would go to C, then D, then C, then D, then C, then D, and they would all get back to B, and then B would formulate them and send them on. You okay? Path determination is the process by which a router will pick the best path to get to that destination. There are three different types of determinations. You have no route determined, directly connected, or remote. In other words, did I set it up as a direct connect? Did I call Lance and have that direct connect with Lance? Or did I ask Bryce what Lance's number was? And he can relay the information to him. Or I don't even have a phone book and I have no way to contact Lance. That would be no route detected, or no route determined. Okay, does that make sense? The switching function of the router. Basically, now we're back down to the layer 2 at the MAC address layer. It's going to strip off those layer 2 headers so they can get and determine the IP address for the destination and the source, recapsulates it back in an IP packet, and sends it on. Any questions? The source and destination IP addresses never change. Only the MAC address. Why? The source and destination MAC address is from the hop to the hop. So, from right here, this physical, to here, in this area right here, it goes from this MAC address to this MAC address. So that MAC address can read it. It opens up, sees the IP address, re-encapsulates it, and sends it back on. Or until time to live is 0, then it just drops the packet. All right, I'm not going to go through that process with you. Basically, this is just going over with what I just told y'all. Any questions on Chapter 1? Give you a basic understanding of what that's about. Static routing. I can sum this all up in very simple terms for you. I need to get to 192.168.3.1 with a mask of 255, 255, 255, 0. Okay? And I'm at this router. All it's going to do is say, this next segment here, what interface am I going out? In this case, this is a WAN connection. I can't draw that, so we're going to call this the 2.2 network. So I have a .1, .2. I could say this is going to be serial 0, 0. Serial 0, 0. That's it. Static routing. That's all it is. What IP address and subnet mask am I trying to go to? Leaving what port? That's it. That's static routing. Pretty simple. Instead of getting you all confused with Cisco's way of 45 minutes of static routing, that's it. Your destination's IP address and subnet mask, and what port is that router sending it out to go to that destination. The ultimate destination, what on this particular router, what port am I leaving? All right. Now, if it asks for a default route, going out what port? All right. Default routes will always be 0000 0000 in what port you're going out. Always.
So 80.
8 zeros. It'll always be the destination IP address. Default route, I don't care where it goes. You use that when you only have one way to one hop out. Okay. So if you go and you look at, if you were able to break into your iOS on your Linksys or your Netgear or whatever router you have at your house, your default, you will have a default route of 00000000 out, whatever your IP address is for your live IP address, or whatever port it's going out. All right? That's what it's for. It's saying anything that's on this network, it's got to go out this port. That's all I've got. Static routing. Same thing, except you're specifying an IP address or a network for it to get to. Does that make sense? Now, I can change this down to 255 all the way down, and you can go to that specific IP address. Usually, that IP address is going to be on a network, so you just keep it up at a network range. All right? All right. Now let's talk a little bit about dynamic routing. What is the functionality of dynamic routing? It's to dynamically share information between routers. Pretty simple. To find the best way to get from one location to another, and to update that information. You know, a perfect example of this I like to use is telemarketers. They know the second you change phone numbers. And they like to call you like crazy, don't they? Mm-hmm. So they got that best way to get, or debt collectors or whatever. They have that best way of finding information out about you, and they automatically update their information because it's dynamically shared to them. When you go to AT&T or Verizon and you get a new cell number, they say, okay, here's a new cell number. The purpose of a dynamic route is to discover remote networks that you don't already know about, maintain that up-to-date routing information table, choose the best path to transport from one router to the next, and if there's a new path, to determine whether it's going to be the best path or not. Okay? Pretty simple, right? The components of a routing protocol are the routing protocol message and the algorithm. What are the advantages of static routes? It's easy to configure. It's real secure because it's direct. The disadvantages is the fact that if something updates, you lose a link, you're out of luck. And it's not scalable. So we have different types of routing protocols. We have IGPs and EGPs. IGPs are your interior gateway protocols, and your exterior gateway protocols are your EGPs. Your exterior gateway protocol is going to be your border gateway protocol. Why? That's to the exterior of your network. Does that make sense? Border gateway protocol, the exterior part. Inside of interior, we have link state and we have distance vectors. Okay. Notice we have this little cool drag and drop functionality in CCNA, so you can kind of get to see what a test would look like. Tell me which ones are which. Well, y'all don't know. But you have distance vectors, which are going to be your RIP, your EIG, or RIP, RIP2, your link state is your OSPF and your is. You have RIP, RIP2, IGRP, and EIGRP. An autonomous system. Basically, it's just a group of routers under the control of one authority. So when I give a distance vector protocol and I say my autonomous system number is 101, that autonomous system number is given by the IANA to you, and we'll go over that. All right? All that means is all these routers are under one person's control. And basically an interior gateway protocol, or IGPs, are used for routing inside of that autonomous system, inside of that one number. So if I say all my routers all my autonomous system is 101, all routers that are attached to 101, that's what RIP and EIGRP and OSPF areas will cover. They're all interior. Exterior goes between those autonomous systems. Does that make sense now? You'll kind of see that a little bit. Now we have two different types of interior gateway protocols. We have distance vector and we have link state. Your distance vector are routes that give a distance and direction. And then you have, but it doesn't give you a great view of your network. Okay? It generally gives you periodic updates. So is distance vector a really good thing to use? Maybe in your local environment, but not over the bigger area. You'd want to use a link state because it depends on the link. If that link is on or the link is off, will complete a view of a network topology. The updates are not periodic though. Okay? So each of them have their pros and cons. Link state, you have a database on each different router, looking for the links out of each port to say whether they're up or down. Okay? Classful routing protocols do not send subnet mask updates. Why? Because they're full. Classless do send it. So that's going to be the difference. Convergence is defined when all routers using router tables are at a state of consistency. That means all these right here show the exact same thing they need to know. Okay? Metric, like we just talked about, it's either your hop count or by your link. You can do it with bandwidth. Now that we're not doing static and we're doing dynamic, I can do cost, I can do delays, I can do loads, I can do reliability. There's a lot of different ways that we can use metrics to see how fast to get something to one place or another. The metric field table is this number right here where you have the 120 and then you have the /2. Okay? Remember, each different type of protocol uses a different type of metric. RIP uses hop counts only. The IGRPs use bandwidth. They use delay. They use load. And they use reliability. Is, and OSPF use cost and bandwidth. Make sense? Load balancing. What about load balancing? It's the ability of the router to distribute packets among multiple same cost paths. So if the paths are both here at 1, then it can go to either one. What's the purpose of a metric? To define the best path to get there, right? So what we have, what we call is an administrative distance. Administrative distance will tell us how long should it take from this router to this router, or from this router to this router. Okay. Now, router 1 and router 3 don't speak the same protocol. Router 2 has to forward it between them. So the first number in the bracket that you saw on the routing table is what we call the administrative distance. Okay? Here are some of the administrative distances. If it is a static, it will be 1. If it's just a connected one, it'll be a 0. EIGRP summary route, you'll see 5. So if you're looking at it, it'll tell you automatically what kind of route this is. If EIGRP, it's a 90. What does that tell me? Well, that's just a regular EIGRP. It's not the summary route. What about 170? Well, that's my external EIGRP. So, and if they can't figure it out, it's going to be a 255. You will need to know this table really well if you plan on taking your CCNA. If I want to show my IP route of this, it'll give me a distance and it'll give me a metric. Okay? The administrative distance of a static route has the value of 1. So let's look at this. They're directly connected, right? And we have this static route. What does it tell me? What's my administrative distance?
1.
1. What does the 0 stand for? It's connected. Remember, this is connected. It's not a static. It's a connected. You can have 1, 1 if it was a static, right? Let's say this had been a 3.0. It would have been a 1-1. Or 1/1, I'm sorry. Any questions on how to look at that routing table?